In this lecture, we're going to continue our discussion of electrochemistry. We'll continue our discussion of the relationship between Gibbs free energy and cell potential and elaborate with the Nerst equation. Next, we'll talk about what some of these calculations look like for electrochemical cells that are under non-standard state conditions. And then we'll discuss concentration cells, so how we can use a difference in concentration to create electrochemical work. So we've been using this example quite a bit so far, this electrochemical cell where zinc is being oxidized, copper is being reduced. So let's just review this equation really quickly. Delta G naught is equal to negative N times Faraday's constant times the cell potential. Remember that this naught symbol indicates that we're under standard state. So we've got 1 molar concentration, we're at 25 degrees C, and we're at 1 atm. But it's the concentration piece that's really important when we're thinking about electrochemical cells. Remember that we defined Gibbs free energy as the maximum chemical work that a system can do. So in this context, delta G naught is the maximum electrochemical work or electrical work that can be done by an electrochemical cell. The work is going to be equal to -1 times the cell potential multiplied by the charge. And we know that the charge is equal to the number of moles of electrons times Faraday's constant, which is the charge for 1 mole of electrons. So that's how we get this equation. Delta G naught is equal to -NFE. This is just the expression of this maximum electrical work that can be done by an electrochemical cell. And this is just a reminder that if E naught is less than 0, delta G naught is positive, so it's non-spontaneous. If E naught is greater than 0, then delta G naught is less than 0 and it's spontaneous. Okay, let's just remind ourselves of a couple equations from Gen Chem 2. So this one we just introduced, delta G naught is equal to -N, number of moles of electrons times Faraday's constant times the cell potential. We also have previously defined in Gen Chem 2 that delta G naught was equal to -RT natural log of K. So we can equate these two sides and say that -NF E naught is equal to -RT natural log of K. -1 from both sides of the equation cancels out, and we can rewrite this as the cell potential E naught is equal to RT over NF times natural log of K. And everything but N is a constant if we're under standard state conditions. So we can rewrite this as E naught of the cell is equal to 0.0592 volts divided by N, where N is the number of moles of electrons that are being transferred, times the log of K. We can go one step further. So remember that we introduced in Gen Chem 2 that delta G is equal to delta G naught minus RT natural log of Q. So remember, delta G naught is when we're under standard state conditions, which usually we're not under standard state conditions. So delta G is telling us whether or not the reaction is going to proceed spontaneously under non-standard state conditions, or it sort of gives us a snapshot of what's going on during the reaction. So delta G is equal to delta G naught minus RT natural log of Q. So we can rewrite delta G and delta G naught to say that this is -NFE is equal to -NF E naught minus RT natural log of Q. So if we factor out -N times Faraday's constant, we can get E of the cell is equal to E naught plus RT over NF times natural log of Q. So again, this cell potential is under non-standard state conditions. And we get E of the cell is equal to E naught of the cell minus 0.0592 volts over N times the log of Q. So notice we've gone from natural log to a log base 10. So this is the Nerst equation. and it's how we calculate the cell potential under non-standard state conditions. Cell potential under non-standard state conditions. So let's go back to our example of our zinc and copper voltaic cell. The overall equation is zinc metal plus copper 2 plus going to copper solid plus zinc 2 plus. So if we wanted to write out the expression for the reaction quotient Q is equal to the ratio of our aqueous products divided by the aqueous reactants. So we have concentration of zinc 2 plus divided by concentration of copper 2 plus. Remember that we calculated the cell potential under standard state conditions was positive 1.103 volts. So that means that if we have concentration of zinc 2 plus is equal to the concentration of copper 2 plus, they're both equal to 1 molar, then the cell potential will be 1.013 volts. But we often will not exactly have 1 molar concentrations of both. So we can use the Nerst equation to calculate the cell potential under non-standard state conditions. So you can imagine if we started out with a cell where the zinc 2 plus concentration was less than the copper 2 plus concentration, so Q is less than 1, so log of a number that's less than 1 is going to be negative. So this whole number will be positive. So that means that the cell potential is going to be greater under these non-standard state conditions. So the cell potential will be even higher. So let's do a quick example. We know that under standard state conditions, this reaction is going to spontaneously proceed to the right. But we want to consider, okay, what if we started off with a copper 2 plus concentration of 5 molar and a zinc 2 plus concentration of 0.1 molar. So we're going to go ahead and use the Nerst equation. Now remember that it's 2 moles of electrons that are being transferred. So I'm going to put 2 here. All right, if we do this calculation, we should get E of the cell to be 1.15 volts positive. So that means that it's going to be spontaneous in the forward direction to plate more copper onto that copper electrode. And we can look at this chart. This is a chart from your textbook that shows how as Q becomes smaller and smaller and smaller, E of the cell is increasing. So here, the example we just did, Q is 0.1 over 5, which is 0.02. So if we look here, we're somewhere around this 10 to the negative second, somewhere around, like about right here on the curve. So the calculation matches up. We got about 1.15 for that. So this is the cell potential under non-standard conditions. So you could also imagine a scenario. So even though E naught of the cell is positive, we know that this reaction is going to be spontaneous under standard state conditions. You can imagine a scenario where Q was so large, this reaction would become spontaneous in the reverse direction. Okay, finally, we need to discuss concentration cells. So with concentration cells exploit the effect of concentration differences to create a cell potential. So concentration cells, you can have copper, for example, on both sides for both the anode and the cathode. But as long as there's a concentration difference, there can be a cell potential. So for example, if we have copper that's being oxidized on the anode and copper that's being reduced at the cathode, and so at the anode, it's going to be the dilute concentration because we're going to want more of the copper to go into solution as a cation. And on the cathode side, we're going to have a pretty high concentration of copper. So this is going to, if you think about Le Chatelier's principle, is going to shift this reaction so that it's going to produce copper solid. So as long as the concentration solutions are different, the cell potential is greater than 0 and the cell can do work. So in this example, we've got 0.1 molar copper 2 plus at the anode, 1 molar copper 2 plus at the cathode. And so there is a cell potential of 0.03 volts roughly. So I want to do a quick example of a concentration cell. So here we have a voltaic cell. And in this example, we've got a silver cell. So we've got silver plus ions on both sides, and then nitrate is the anion that's a spectator ion that's floating around. So on the anode side, we have the more dilute concentration, the 4.0 times 10 to the negative 4th molar. And on the cathode side, we have the more concentrated 0.01 molar. E naught is 0 because we have the same reduction potential for both the anode and the cathode. Both of them are silver. So both of them, if you looked them up, would be Ag plus an electron going to Ag solid. But the overall reaction is Ag plus Ag solid, forming Ag plus Ag solid. Okay, so if we want to write out the Nerst equation, remember we said that E is equal to E naught minus 0.0592 volts over N, which in this case is just going to be 1, times the log of Q. So Q, remember that your anode is what's being oxidized, so that's going to be the product. So the product's going to go in the numerator, so we have 4.0 times 10 to the negative 4th divided by 0.01. So Q is equal to 0.04. Whoops. So E is going to be E naught minus 0.0592 volts times the log of 0.04. And remember that E naught is 0, so E is equal to negative 0.0592 times the log of 0.04. So we get a cell potential of positive 0.083 volts. Okay, so this is just an example of how you could use concentration differences to generate a current.